In this video, I'll be going over improving the trunk lengths in mini elephants of a population. So we start with our initial population of 100 of our mini elephants. I see that they have trouble reaching food that is more than 6 centimeters off the ground, and I want to be able to breed the best mini elephants I can to increase profits. I decide to perform an experiment that I think will increase the length of my elephants' trunks, making them more sought after and increase their demand. To start the experiment, we're initially given that the broad sense heritability, big H squared, is 0.85 and its realized heritability, little h squared, is 0.67. We take all 100 of the elephants and find the average trunk length for the entire population. We find the average x naught to equal 2.68 centimeters, and with a standard deviation of 0.5 centimeters. We then plot these values using a histogram where the x-axis gives us length in centimeters and the y-axis gives us frequency. We are also told that the proportion that we're going to use for breeding is 10%. Given x naught, we can then find the truncation point x sub t. We're given the equation x sub t equals initial mean plus z times the standard deviation sigma. But what is z? Z is the standardized selection point and is based on the proportion you take from the original population. We can get this value from this table. We took the top 10%, so z equals 1.282. After calculating it, we find the truncation point to equal 3.321. Next, we can find the selection differential S. We're given the equation S equals I times the standard deviation sigma. Looking at the same table as before, it also shows the value for I, selection intensity. We took 10% of the original population, so I comes out to be 1.755. Plugging that into the equation, we get S to be 0.8775. We can then use this to find the mean of the sample population by the equation x sub s equals s plus x naught. So we have 2.68 plus 0.8775, and we get x sub s to be 3.5575. We now have the selection differential S, which is equal to 0.8775. The next step is finding R, which is given to us by multiplying the realized heritability by the selection differential. Remembering that our realized heritability is 0.67, we can go forward with our calculation. We find R to be equal to 0.5879. We can then find the average trunk length of the offspring x sub 1 by adding the response from selection R and the mean of our original population, x naught. We have 2.68 plus 0.5879, which means our average offspring trunk length comes out to be 3.2679. The new graph shows how the offspring population would be normally distributed. Over time, the selection of our response would decrease because the trunk length will get to the point where it may actually be heavier than the animal and causes more problems than helps.